Hello everyone, welcome to the YouTube channel, welcome to the video, thanks for stopping by. So this talk, this lecture, I originally gave it a few years ago as part of UCU Strike Action, and then I updated it because it was actually a good idea and gave it again for the latest round of UCU Strike Action. So it actually comes from a place of considering the economics of society as a physicist. But it struck me after chatting to some first year physicists that this sort of thing really shows the power of a physics education. It's not just understanding how the universe works, right? Which is pretty good. It's not just being able to answer the questions that your parents ask when they've been watching Brian Cox on TV, for example. It's not just about being able to mic drop after you've said some really deep and fundamental equation. Physics is about being able to model things, anything. It's about an understanding of how knowledge works. It's about an understanding of the scientific method, right? So it's not just about springs and atoms and all the things that you're learning. It's not just about mechanics. It's about being able to apply mathematical, physical models to everything around us, and that's what really brings all of the sciences together: physics, chemistry, biology, and the social sciences as well, right? So sociology, economics, and the other social scientists do this as well. So what we're going to do here is apply physical models of systems that we know and love to the economics of the world around us. So it's a conversation between lecturers and students. So if you're one of my students at University of Leeds, hello, come and grab me and talk to me about this stuff whenever you like. I quite like it. If you're not, I don't know if this is on YouTube, leave a comment, like and share and all that sort of stuff. Okay. Oh, final disclaimer. Physics is about modelling, but it's also about experimental evidence and data, right? So I'm going to say that what I'm about to present in this talk, this lecture thing, is a hypothesis. It is not a theory. It is a few things I've noticed that I think deserve some experimental attention in society. So this model that I'm about to propose is a hypothesis and a hypothesis only. It is not true. It is only true if experiments exist that can verify the predictions of this model, right? So with that said, let's begin with the physics of economic equality, or post-ironic multi-scale biophysical economics, right? That's what it's really called. So first of all, who am I? Dr. Ben Hansen. My field of interest is computational biophysics. So that means I'm interested in biological mechanics, how cells work, how the scaffolds that hold cells up work, how things diffuse throughout the body, how force is generated internally to the body. Gels, molecular motors, so they generate force, and also the crazy abstract maths involved in that sort of stuff. But I'm also interested in the philosophy of science, science communication, and the perception of science at large. That's an interest of mine. Now, I work at the University of Leeds, but the things I'm saying here in no way represent what the University of Leeds thinks as an institution. However, they pay me to think about these things, so take from that what you will. Maybe the more appropriate things are the Twitter handle there and the website if you're interested in these sorts of thoughts that I'm having. Okay, so let's move straight into the ideal gas. First year physicists at the University of Leeds have learned about the ideal gas in the last couple of months, so they'll know all about this. But for those who don't know about this, let's go forward. Fog. Fog is a gas, right, or a vapour. I've used this as a metaphor because you can't see the trees for the fog, right? That metaphor is going to become apt as we go through this talk. But for now, let's just think of a gas, right? Fog's a gas, oxygen is a gas, hydrogen, it's a gas. It looks a bit like that. The macroscale model for a gas that we talk about in physics and other sciences is called the ideal gas equation. Now, there is a non-ideal gas equation for complicated situations, but for now, let's just think about an ideal gas. And the ideal gas equation is this: PV equals nRT. So, just for a moment, let's think about what these symbols mean. P is pressure, V is volume, T is temperature, N is the number of moles of gas, or the amount of gas, where volume measures the actual space it takes up. N is the number of particles in that gas making it up, or the number of moles of gas particles making it up. And R is simply a constant which brings all of these things together. That's called the gas constant. So, let's think about what this means. It means that the pressure of a gas pushing outwards, because a gas tries to expand, it has pressure, it pushes outwards, multiplied by its volume, is equal to something to do with the temperature and the number of particles multiplied together. That's interesting. That's a model. If we do experiments on the pressure and the volume of a gas, we will find it is related to the temperature and the number of things making up that gas. But what's perhaps more interesting is if we look at the left and right hand side of this equation, we might notice as undergraduate physicists that PV, pressure times volume, is work done. It is the amount of energy, the amount of active effort that gas is able to exert on its surroundings. So it's an energy. And that means that what's on the right hand side is also an energy. It's thermal energy. It's related to the temperature, right? So what we actually have here is energy calculated one way is equal to energy calculated another way. And then it starts to make sense. That's what our macroscopic model is saying. That these measured things equal these measured things. Nice. That's what the ideal gas equation is saying. The work done by gas on its surroundings is equal to the amount of thermal energy it has. But what are these things, right? What is thermal energy? What is pressure, volume? What are these things at a fundamental level? Well, oops, I can go back one. So if we look at these things, zoom in on that gas, zoom in to the individual particle level, right? A solid might look like this. Solid is loads of particles very, very strongly bonded together. They're not moving that much. A liquid is a load of things quite loosely bonded together, but there's still a lot of them. They're still quite closely connected, just not as much as a solid. A gas, though, is where the interactions between particles are very weak compared to liquids and solids. And because of that, all of the particles are quite far apart from one another. They move almost independently of one another, and they bang into each other occasionally. That is interesting. As a computational physicist, I can do a simulation of these things, right? I can take a box, and you can just see it there with a little green outline. There's a cubic box there. You'll see it when the movie starts. I can take a box, I can fill it with some number of particles. I can give those particles what we think their energy should be at the microscopic scale. And we can measure whether this model holds up at the microscale, whether the ideal gas equation comes out of it. So let's look at this simulation. Here we go. Right? So all these particles are moving around, each one independently moving around in a certain direction. It's little random motions. It's called Brownian motion. Each of them are given a little jolt in each direction. And the statistical properties of all these things means that they're going to bang into each other occasionally. And when they bang into each other, they're going to swap energy with one another, like momentum exchange, although in this case it's not momentum. They're going to swap energy with one another. There's certain dense parts and certain sparse parts, but they're all going to move quite randomly. And those dense parts will become sparse, and the sparse parts will become dense. And you get this random sort of dispersion of moving particles. So we've moved into something called statistical mechanics now, which is related to the ideal gas equation, which is thermodynamics. Thermodynamics, the movement of things due to temperature, or the movement of temperature, the movement of energy. Statistical mechanics is what's going on at this scale, the micro scale, the single particle scale. And here we have some equations too. The average energy of each one of those particles is 3 divided by 2, multiplied by something called Boltzmann's constant, Kb, multiplied again by the temperature. So that's the average energy of each one of these particles. It's 3 because this is three-dimensional. The rest of it comes from an analysis of quantum mechanics and statistical mechanics. We also know the velocity distribution of these things. That's the Maxwell-Boltzmann equation. A little bit more complicated, I'm going to admit that right now. Don't worry about any of this. What this suggests is we know that the probability of any particle having some velocity v goes as this crazy equation. And you can see that it's got that kBt in there again. It's got the mass of each particle there. It's got a mass of particle there. V squared there. So that's mv squared divided by kBt. Interesting energy divided by energy. A few other bits out the front. An exponential. Doesn't really matter what that equation is. All that matters is we've got a microscale model, this, and we've got a macroscale model, the ideal gas equation. So, maybe pressure is the collision of each one of those particles with the box, right? The sum of all of those collisions of those particles with the box is the pressure. It's the amount of force pushing outwards on that box, right? The volume is the volume of the box, we get that. Temperature now, we know, is the average kinetic energy of those particles. We can measure it because we know how fast those particles are moving, so we can measure the average kinetic energy of the particles. And we can measure the number of moles, right? That's just the number of molecules in this system. We can measure that, and that's related to Boltzmann's constant. It's related to that thing called the gas constant. Number of moles is related to that. So we can measure that, and it turns out that the models at each scale are related to one another, and they're consistent with one another. That's really important. So I can use that microscale model to deduce what's going to happen at the macroscale. I can calculate the pressure from the microscale model, I can calculate the volume, the temperature, the number of molecules, and I can get the macroscale model back. Equally, if I've got the macroscale model, I can have a very good go at guessing what's happening at the microscale. There's multiple answers as to what's going on, but what's most important is that they're related and they are consistent with one another. Now, these are gas particles wobbling around a box, and they're banging into each other, and they're exchanging energy with one another. Interestingly, human beings wobble around a box. We'll call that box Earth, and they bang into each other. And when they bang into each other, they don't swap energy, they swap money. Interesting. The ideal economic gas. Humans as an ideal gas. Now, there's no such thing as an ideal gas. If you measure an ideal gas in an experiment, you'll find that it's actually not ideal. You have to very much control the environment to make an ideal gas. Otherwise, it's non-ideal. You have to make additions. Humans, too, are not an ideal gas. But we'll see that by treating them as an ideal gas, we can make some interesting inferences, and then we can make some guesses as to what would happen if they were a non-ideal gas. So go with me for a second. Humans wobble around a box. That box is Earth. They bang into each other, and they make trades, exchange money when they bang into each other, right? But the important thing here is through what process do we exchange money? We call it a trade. There are rules to trades. And I don't mean the rules set by the international banks. I don't mean the rules set by the law. I mean when we trade, we have this idea of what it is to have a fair trade, right? We have these sort of implicit rules as to what it means to trade with one another and how to do that fairly. In an ideal gas, or in a gas, when particles bang into each other, they exchange energy and they exchange momentum. Those things are physical laws. They're experimentally measured and almost 100% certain. We know how those rules work, and they're unchangeable as far as we know. We exist in a universe where the rules are whatever they are. Human trading, in principle, we can change the rules, right? We can change what it means to be fair when we do a trade. So we have to ask the question, what does it mean to do a trade when you're a human being? So there's a couple of links here. I've opened up the links. I'm going to put them in the description of this video. But me and this person, Philip Rosedale, who if you Google him, it turns out is quite famous, did some stuff where he wrote a model to simulate human beings as an ideal gas, exchanging with one another by the rules of our society as it currently stands. And what he wanted to do was look at the statistical properties of those trades, just like we were looking at the statistical properties of that ideal gas before and seeing if they align with one another. So he wrote the following simulation. This is the simulation code. You can look at it yourself. What's going to happen is there are going to be a load of particles in a two-dimensional grid. And those particles have a size. That size is their value. Okay, how much stuff they've got. When they bump into one another, it could be a big particle and a small particle. When they bump into each other, just like when humans bump into each other, they can make a trade. Now, what they can't do, they can trade, well, what they can do is they can trade any amount of money up to the maximum amount that the poorer person has, right? So if I've got someone here with 100 and someone here with £10 and they bang into each other, they can only trade up to a maximum of £10, right? That's fair. Why would the person with £100 trade any more than £10, right? That person has £10, that other person has £100, so that's the maximum amount that they can trade. And when they bump into each other, we can imagine that that £10 is actually spent on goods and services, right? In some form or another. So when they bump into each other and they organise this trade, a coin is going to be flipped. And that coin is going to determine which way an amount of money goes. So £100, £10, they bang into each other, someone flips a coin, it's heads, that means that the £100 person is going to give some money to the £10 person. If it's tails, it means that the £10 person is going to give some money to the £100 person. And it could be any amount up to that £10, right? So it's just like some random trade is happening between these two people. Money could go either way, but it can only go as high as the £10, right? The poorest person's maximum amount. Let's see what happens when we run that simulation, right? Here's a load of, it's not just two particles, it's a load of particles. They all start off with the same amount of money. That's interesting. There's no trades happening yet because it doesn't happen for a while. Here we go, the trades have started, right? So red ones are smaller, green ones are bigger. So we might call the green ones the upper class, the rich. We might call the red ones the lower class, the poor. And we might call the blue ones the middle class, the middle, right? And you might see already that there's a lot of reds out there. There are a lot of reds out there. They started out blue and now they're all red, right? Some of those reds are precariously small. The number of greens are also quite small, but they are big. They are taking up quite a lot of value out of this system, right? They're taking much more area of this grid than anything else. And you might also notice that the number of blues is decreasing overall as well. So all this is happening is every time two particles in this system of any colour bump into each other, they're making a trade based on those rules that we said before. And they sounded quite fair, right? That's how we do trades. If you've got £100 and I've got £10 and I say, oh, I'm going to give you £11, I can't give you £11, don't have £11, I can only give you £10 maximum for goods and services. So that's the limit of our trading maximum. And we can see that society in this simulation is growing as society does outside in the real world. If we observe society out there in the real world, we might hear about the 99%, we might hear about money going to the rich and the poor being kept poor. Here in this simulation that runs on these simple rules, this is happening as well. So we might say that this simple simulation here says something about our society because it reproduces some of the effects that we see in society. In fact, we see that the number of reds, they're all extremely, extremely, extremely poor now. They have the minimum amount set in this system, which is 1. I could have set the minimum amount to be 0, but that would be quite depressing. So I set the minimum amount to be 1. which you could call, I don't know, the minimum amount required to live. But you might also notice that the blues, the middle class, is decreasing as well, which suggests that the middle class in our society is a political choice, right? Naturally, if we're allowed to trade freely with one another, as neoliberal economics tells us, the middle class stops existing after a while. It just gets absorbed either into the poor or the rich, and it's basically luck, according to this simulation. And so you see that the number of greens is also decreasing, but there are a few big ones jumping out. In our society, right now, in our world, we can put names to those giant green blobs. In fact, Philip Rosedale did this. Elon, Jeff, that might be Bill Gates down there, right? So yeah, this is an ideal gas simulation, but we've altered the rules of how trades happen. This is not how trades of energy happen in ideal gases, but this is how trades between humans works, right? In an ideal gas, that giant green one right there could bump into one of those red ones and give it everything it owns. Could just do that. It doesn't though, in this human simulation here that we've modelled, so that's interesting. What we can do is alter the rules of trade, right? In this simulation, we can alter the rules of trade just to see what will happen, right? In this simulation, and this is my addition to this, that I took Philip Rosedale's code and made some additions to it, and the additions that I made was to alter the trading rules. I made trading proportional. So that £10 and that £100 bump into each other, and they say that my £10 and their £100 are worth the same, because that's all of our money, 100%. A £5 from me and £50 from the person with £100 is worth the same, because it's half of both of our incomes. We're trading proportionally now. If I bump into someone with 1,000 and I've only got 10, their 500 is worth my 5, because that's half of both of our total incomes. Now that sounds completely unfair, right? How on earth can £5 and £500 be worth the same amount? This proportional trading idea seems completely unfair, right? Unfair. Let's think about what it means to be unfair. Because if I run that simulation where trades are proportional, let's see what happens. They all start off the same. And trades start happening. And trades continue to happen. And they continue to happen, and they continue to happen, and they continue to happen. And it turns out that if you measure the wealth distribution of people here, you get what's called a Gaussian distribution, or something that is statistically fair. So what's interesting here is our notions of fair at the microscale, at the individual trade level, lead to massive economic inequality at the macro scale, which is unfair, potentially. Some people might not say it's unfair, but we'll get onto that soon. However, what we've seen here with this simulation is that if you create a rule of trading that is unfair at the micro scale, it leads to complete economic fairness at the macro scale, right? So that's interesting. That's very interesting. And we can show that if we run this simulation, if we leave it running forever, we'll never get any big greens, we'll never get any big smalls. Any big greens, we'll never get any small reds. And if we do, they won't stay that way for long. So there's a constant motion of energy, of fluid, of energy throughout this system. Whereas in the first system that we saw, that represents our society quite well, all of the energy gets pumped into one or a few single objects. So keep in mind those two things. Keep in mind that how a microscale model can lead to macroscale outcomes by running simulations like this. And keep in mind that idea of fairness at both scales. Interestingly, by the way, if we do the first one of the common criticisms I get on this is, hang on a minute, human beings don't just move around randomly, right? They don't just move around randomly and bang into each other. They actively make choices about who they trade with, right? This is the one where it's fair trading at the micro scale, right? Where everything's absolute. Human beings don't just randomly trade with one another, right? They choose who they're trading with. But let me ask you this. When you choose who you're trading with, do you choose any of those red particles banging around? Or do you go to the giant green particles when you want to do a trade? Do you go... Oh, hang on. When you trade, do you go to Amazon? Do you go to Tesco's rather than your local greengrocers? Do you go to Facebook rather than hanging out and chatting with people just casually, right? When you trade when we trade as human beings, we actively seek out those green particles and trade with them. So if anything, our rational decision-making abilities make this economic equality even worse than just a random series of trades. In a random series of trades, wealth still goes upwards, but it takes a while, whereas right now we actively go and seek out these rich people and give them ever more of our money in exchange for ease of living, but at the cost of decision-making power, for example. Whereas in this one, where it's all nice and equitable, even if we do go and seek out those green ones, it will put money back into the system because we're trading proportionally. So that's something that's worth thinking about there. So let's go back onto the slides. Humans as an ideal gas. Our conception of fairness at the microscale does not seem to align with fairness at the macro scale, or vice versa. So that's interesting, right? Unlike the real ideal gas, our economic models do not align across the scales. What we consider as economically fair, however we choose to model fairness, does not generally align with what we consider to be fair at the macro scale. Fair trades at the microscale lead to massive economic inequality at the macroscale, and weird proportional trades at the microscale lead to what looks to be a nice equitable system at the macroscale. So our models do not align. And so that's going to be a segue into what I actually do for a job, which is simulate the motion of proteins and biological networks. Now, if it kills me, I'm going to get physicists interested in biology by the end of their degree. I'm going to do it because biology is awesome, and I'm going to explain to you why it's awesome. So, what is a protein, right? If this is a physics audience, I don't expect you to know what a protein is. You might think this is a protein, right? Protein powder, that's what it is. You might think this is protein, which is muscle, right? That is what protein is, it's just muscle. But it turns out that in your body, anything that ever needs doing, anything at all, whether that's synthesizing chemicals in your body or digesting things or building muscle or growing bone or thinking, everything in your body that is a thing that needs to be done requires a protein to do it. Even reading DNA. Proteins are made out of DNA, but reading DNA requires a protein itself. Nuts, I agree. To me, a protein looks like this. Right, so this is just a model of a protein done for biologists. This one's I-27, don't really matter what it is, but it's got these arrows on it. Obviously proteins aren't really arrows, they're made up of atoms, but these arrows are just ways of representing the protein so we can sort of understand how it might move. It's more clear in protein L, where we've got that pink thing. That's called an alpha helix. It's got certain spring-like properties, but it's also got some of those things at the back. They're called beta sheets, and they have certain mechanical properties. In fact, we can give each one of the atoms in this object a temperature, just like we did in the simulation of the ideal gas. We can give them a drag, a frictional force in the background. We can give them a mass, electrostatic charge, and we can make them move around just like those ideal gas equations. And by measuring these things as they move around, we can measure their mechanical properties. Interesting, because I-27 is a part of the massive muscle protein titin, and so knowing its mechanical properties might tell us something about how muscles work, right? Protein L has got these two different substructures, so knowing how those different substructures move might tell us something about what this protein does. Interesting. But I am a physicist, and so proteins to me, obviously, are just spheres that can stick together, right? I want to make everything as simple as possible, and I'm not that interested personally on what goes on inside a protein. I'm more interested in how proteins interact with one another. So let's model everything as a sphere with a number of ways that they can interact with one another on the surface. And so if I stick them together at the surface there with pivots or bonds, chemical bonds, because they can't overlap with one another, that's called a steric clash, that means that stiffness emerges just from the structure of these things, which as a physicist is super awesome. Emergent properties, check this out. 3 polymer simulations, same spheres, different ways of sticking them together, and we can get a flexible polymer, a semi-flexible polymer, and a rigid polymer, just from the emergent properties. Amazing. Small little side note, when I first started working at the University of Leeds for Lorna Dugan, who's on this paper at the bottom, she was worried that I wasn't doing anything because I spent ages writing a simulation platform. Turned out it was okay to spend ages writing a simulation platform because we submitted this work to a journal and it got accepted and published within like a month. So that's pretty awesome. So this stuff's good. It is good. It's been peer reviewed and they say it's good, so I'm going with it. What's more interesting though is that I can get networks of these things, right, and make them start sticking together. So here's the network of these things. I'm going to run this video from the start. Right, so all these things, it's that ideal gas simulation, except each particle is now a protein and it can stick to other ones as the simulation progresses, right? If I run this video, look at that. They all stick together as they're randomly moving around the system, and they form these really complicated fractal patterns. In fact, that's not enough particles. This is enough particles. And they still form these massive fractal patterns. Check it out. Beautiful patterns formed just by things moving around and sticking together when they bump into one another. So we've got these microscale rules. Proteins are spheres. They have a number of sites on the surface, and when they bump into each other, they can stick together. That is microscopic rules. And we get these macroscopic objects forming out of them, which is awesome. Simple models then can generate complexity, and simple models can help us to predict complex reality. Are you seeing the metaphors with the society models that we've been doing so far? I think I am. But what's interesting is that this is the theory, right? This is the theory bottom up. We've got these simulations. We've got these mad equations determining how things are happening. That is maths, prediction, deduction. But if I'm predicting things, I need experiments to measure whether my predictions are true or not. So colleagues of mine at the University of Leeds use these things, rheometers, which just measure friction and mechanical properties of these things at the macro scale. By the way, these things on the left are called colloidal gels, or in our case, protein hydrogels. Have a Google of that, they're super interesting. But you can measure their properties at the macro scale, and you can see whether or not whether they agree with one another. But what's interesting is that no one knows really what's going on in the middle. So you've got this stuff at the micro scale, you've got this stuff at the macro scale, but how it gets from one to the other is currently unknown. There's a missing step in the middle. A missing step. And that's called the mesoscale. And this is actually another frontier of physics. You know, you hear about the frontiers of physics being quantum mechanics and relativity, but the biological mesoscale is another frontier of physics where the mathematics is so complicated, we have no idea what's going on, generally speaking. Some people are having a good go, like me, my colleagues, but equally, economics, right? We've already said that the macroscale and the microscale models don't align with one another. Something to do with our conceptions of fairness at both scales are misaligned. So something's going on in the middle, right? Mesoscale economics. If you've got an individual here, whether they're a particle or a human being, and we zoom out, and we zoom out, and we zoom out, and zoom out and zoom out, all of a sudden we can't see the individuals anymore. So at some point the individual model becomes this macroscopic continuum model, right? Like this. This is another protein. Stick 4 of those proteins together and you get a bigger protein, but it's still a single protein. But if you stick loads of these together, you find blood cells, right? Very, very different objects from this. And if you stick loads of blood cells together, which are singular objects with mechanical solid properties, you get a liquid, right? So something is happening at the biological mesoscale here to take single objects into liquids. Equally, something is going on in economics to turn individual human beings into collections, nations, companies, whatever, right? Our job, my job as a mesoscale computational biologist, is to understand how one model transforms into another. So this is a simulation of a biological molecular motor called cytoplasmic dynein. And I can say to myself, right, maybe I don't care about all the atoms in this model. Maybe there's too many, right? Maybe I'll just care about the shape. And here we've got something called a finite element model, which just takes the shape, not the atoms, not every single individual atom, just a general shape, and gives it some loose mechanical properties like a Young's modulus and a shear modulus, and I can get the same behaviour out. So that tells me something about what's going on in between these two models. Interestingly, that model on the right is how they animate video game characters. It's roughly speaking the same mathematics. And I can do the same thing at higher energies. So this one again is sticking to the surface of that thing above it. That's called the microtubule. And I can make a continuum model that does exactly the same. So that's telling me something about what's going on in the middle. And that's all about the interpretation, right? Is it discrete atoms or is it a continuous wobble? Who knows? Maybe it's both, but it depends on how we interpret the model. So this idea of money as energy has not gone unnoticed by policymakers or economists or politicians, right? So here's a microscale model. Discrete people. Here's 2 people. They're trading some money, right? We saw that simulation of this. Here's 3 people. They're trading money. One of them is angry, right? So maybe they're getting a bad deal. Here are a lot of people trading money. It's starting to get a bit difficult. It turns out that if you try and hold more than 7 objects in your mind at once, I think it's 7, might be 9, but if you go beyond a certain number of objects in your mind and try and distinguish them, you actually can't do it anymore. You subconsciously start grouping things together. Try and remember a telephone number 1 digit at a time. You won't be able to do it, but if you try and group it into 3s, you will be able to do it. And so our memory is built around grouping things together to make it easier to interpret data. So individual models containing discrete people, we can talk about individual supply and demand. We can talk about how much each person wants of each item and how much they're willing to trade one for another. So I learned my undergraduate economics, if you like, from MIT in America, who put out all of their material for free. And the guy who does those lectures always talks about the trade-off between pizza and movies, right? If I can rent a load of movies off Netflix or Amazon or something like that, how many am I willing to trade to get a pizza, right? So we can talk about individual supply and demand and how they offset each other given certain budget constraints. Budget constraints are our wages. How much do we individually get paid for what we do in our jobs or as independent business owners or as students? How much do you get individually in stipends or from your parents, things like that. We talk about personal wealth and savings. We talk about how much money we have got in the bank. What are our individual assets? Do we own houses? How much are we in debt or credit? Importantly, tax pays for communal services, right? So when we're taxed by the government, we have this idea that our tax pays for the services that the government provides to us, whether it's the NHS, the police, the fire brigade, the military, having your bins taken out when you pay council tax, voting, anything that we pay for, with tax is a communal service, or so we think at the micro scale. But let's send all these people over here and just say, okay, those top two, that's one group, and that one over there is another group, and that one at the bottom is a big group, right? They're different groups of people. We could even go one step further and say, actually, that's just one big continuous group of people, right? Let's imagine that there are more people than that. This thing sort of looks like the structure of a country, right? Or maybe it's a representation of the financial flows across the entire world. Notice there that I said financial flows, right? Because at the macro scale of economics, we no longer talk about individual supply and demand or wages or personal wealth. We don't talk about money in absolute terms. We talk about economic potential, right? We talk about financial and capital flows, long and short term. We talk about sources and sinks of wealth, right? So for an example of a source of wealth, we might think of somewhere that's just struck natural resources, right? Oil or something like that. In the future, the Sahara Desert might be a source of wealth because that's a massive space that you can put solar panels in at very little cost, a source of wealth, right? We don't talk about the individual things. In fact, just like individual, in blood as our example, or in any liquid, we can talk about the individual atoms in that liquid, but we don't talk about the individual atoms in that liquid. We talk about liquid as a whole. Liquid has what's called a fluid potential, which tells us how it's going to move. It has a flow rate, it has streamlines, it has streak lines, things like this. Fluids have sources and sinks. Where's that fluid coming from? Where is it going to? We don't talk about the individual atoms because there's too many. We just talk about the fluid as a whole and how it's moving. And this is how money is talked about at the macro scale. Here, then, tax is not for communal services. It is for financial redistribution. Its function is to offset those unfair trade rules that we saw in the simulation examples and to put money back into the system. And so the interesting thing for us here is, how does the microscale and the macroscale link together? Is there something going on in the middle that's mesoscale economics, right? And so we have to think about interpreting these things. What does a model mean? What does it mean when we model society as a group of individuals compared to modeling society as a continuous structure where money flows from one region to another? Well, the interpretation problem arises when single people begin to amass the wealth of nations. Let's look at those people, shall we? There's 5 people who have so much wealth that it is comparable to the wealth of nations. So how do we model these people? Are they individual, discrete people? Do they get wages? Do they have individual supplies and demands? Is their tax paid for communal services? Or, because they have the wealth of nations, are they continuous macroscopic economic objects? I argue that they are the latter. But what is really interesting is that because these are individual, discrete, microscale people with the wealth of nations, continuous macroscopic objects, people get confused, just like with Bose-Einstein condensates, where our models of reality no longer work. Bose-Einstein condensates are things that exist at the macro scale with quantum mechanical properties, and when people look at them, they say, hang on, that looks like a liquid, but how can it be a liquid? Because it's climbing up the side of the glass that it's in. It looks like it's got wave properties on the top, but gravity's not doing that. What on earth is... Bose-Einstein condensates are quantum mechanical objects existing at the macro scale. And because there are 2 models overlapping with one another, it confuses people. And I argue that these individual human beings also confuse people and prevent them from making appropriate political decisions. And all of that comes from my understanding of physics, of experiments, of data, and of how to apply models to different systems. So here's an idea. It doesn't matter whether these people are philanthropists or whether they earned their money. We don't even need to consider why they're all white men. That's a whole thing, but we don't need to consider it here. What we're going to consider is that these concepts, earning money, individual philanthropy, who these people are the language of microeconomics, whereas these people are macroeconomic objects. That does not mean that they are ethically in the clear. It means we need to treat them differently in order to apply our models of fairness and our models of ethics appropriately. So, oh yeah, a little side note, these men are rich because they own the networks between people. So if you've got N people in a network, all connected to one another, turns out that there are half n squared minus n possible connections between them. And because of that n squared term, it grows much faster than the number of people in the network. So if you can control and monetize those networks, then no single person or collection of individually acting people can possibly compete with them. They simply grow too quickly. Academic publishing companies also do this at a massive cost to the taxpayer. Academic publishing companies control the network of connections between scientists, and so when scientists try to communicate their research with one another, they are absolutely ripped off financially by academic publishing companies. And this is well known, but it's very, very difficult to combat. And this is also why this talk was originally given as part of the UCU strike action, because universities control the connections between students and academics. And it's worth thinking about what that means. So, oh, by the way, disclaimer, that's not the University of Leeds' fault. Their policies actually try and alleviate this, but they're trapped in a system that they can't escape. Let's move past that. It's all about the interpretation. Here is a model of the 99%. And let's model the 99% as a fluid. There's a vector field. I've drawn it as a vortex on purpose, right? That's a vector field representing a continuous liquid of money, in this case, of economic potential. Here's Jeff Bezos. He exists independently of the 99%. We can isolate Jeff Bezos and his wealth, and we can say that he's in internet and logistics, right? And that's a network between people, right? Interestingly, by the way, if you didn't know, Amazon makes most of its money not by delivering parcels, but with Amazon Web Services, AWS. So they control the entire, not just the physical logistical network of how we deliver stuff to each other, but also most of the online logistical internet traffic between businesses in the world. So Amazon also control the internet. So that's nice. This is Bill Gates. He's in hardware and OS. So that's how people use hardware to communicate with each other. Here is Warren Buffett. He's into random investments. Of all of them, he's the most philanthropic, but he can't give his money away fast enough, and we'll see what that means soon. Here is Zuckerberg. I am almost convinced that Zuckerberg is a robot, but we'll go with it as a human being for now. I believe that this man is in advertising. He's not in social media. He sells our time for advert space, right? He sells our time to advertisers for money. So he's in advertisement, and the way he gets our attention is through social media, but he is in advertising. That is his job. Here's the last one. Memes. I have no idea what this man is doing. Twitter. I do not know what he's doing, but he's there. So this is a system. It's a thermodynamic system, right? Because it's liquid. Money is liquid. It behaves like a fluid. It has fluid-like properties. We've seen that. But what's interestingly is that statistical mechanically, the second law of thermodynamics says that things redistribute unless work is done to prevent that from happening. So temperature moves from hot to cold, right? Temperature spreads out. If you've got a hot thing at one end and a cold thing at one end, it will eventually all be the same temperature. That's one of the laws of thermodynamics. If you've got two things in contact that are the same temperature and a third one, they're all the same temperature. Things even out. That is the second law of thermodynamics. Things even out unless you put effort in to stop them from evening out. But these people are putting in that effort. In fact, it might not be them. It might be the system itself that's set up this way. They are dams of wealth, but they're not just dams. They're Maxwell's demons, which have been shown to not exist in physics. Maxwell's demons cannot exist unless effort is put into the system to allow them to exist. So these people are the societal equivalent of Maxwell's demons, because what they do is they suck money out of society, and they can't help it. Bill Gates gives a lot of his money away, and it just comes back to him, right? He can't help it. He exists within a system that can't help but give him money. And that doesn't make him ethically in the clear. He has the power to disrupt this system entirely. He chooses not to. Or maybe he doesn't understand. I don't know. But he can't help but get his money back. Jeff Bezos is another example. There is no way he could spend his money that wouldn't eventually get back to him, right? He's going to pay his staff. His staff are going to use that to buy things from Amazon. Goes back to him. He's going to use the internet. That internet is going to be built on AWS. It's going to come back to him. He can't spend money without it coming back to him. He just can't do it. That doesn't make him ethically in the clear. He has enough power to disrupt this system. He chooses not to. Of all these people, Musk definitely understands this. He understands post-irony. He understands how this system works, and he's actively doing it. He thinks it's funny. He's wrong. It's not funny. And so perhaps it isn't about deserving wealth, right? Bringing these models together, this idea that the microscale and the macroscale are models of fairness don't apply to one another. In fact, our models don't even align with one another, unlike the pure physical models and statistical mechanics. Perhaps it isn't about deserving wealth after a certain point. The idea of being paid for your work only works as a microeconomic model. Indeed, it's been noted by psychologists that after a certain point, money doesn't even make you any more happy. You get to a certain amount of comfort and then extra money just does nothing. So if someone says that Bezos earned his money, there's a typo there. If someone says that Bezos earned his money, that statement doesn't even make sense, because they're applying the language of a microeconomic model, the idea of earning money, to a macroeconomic system. Jeff Bezos. I argue that we need to start treating these people as macroeconomic systems in order to effectively understand what's going on and regulate society in a way that makes it equitable for all. If someone says Bezos earned his money, that statement doesn't even make sense. The language of the sentence is incoherent because they are implicitly applying a model to a system where it doesn't apply. Saying that the ultra-rich earned their money in the modern economy is equivalent to trying to define the temperature of a single particle. It is illogical and it is incoherent. So, thank you very much. Thank you. If you've got any questions on this, come and grab me if you're one of my students, or leave some comments in the YouTube doobly-doop down below. Thanks a lot.